All right, this is a video on linear equations and slope-intercept form, and in particular today we're looking at a challenge and then a real-world connection problem. I encourage you to pause this video and try these on your own, see if you can get them, and then unpause, check back in, and see how you did. So our first problem we'll do on the left, find the area enclosed by the following four lines. X equals 0, y equals 0, y minus 4 equals 2x, and y equals 7 minus x. Okay, let's see here. So it looks like x equals 0. I'll try to color coordinate a little bit. X equals 0 is the y-axis. Y equals 0 is the x-axis. I assume we'll have, just looking at the graph was set up showing us quadrant 1, right? So I assume everything's going to be in quadrant 1, but we don't know for sure. Next, y minus 4 equals 2x. So this is y equals 2x plus 4. So let's graph that up. A y-intercept of 4, 1, 2, 3, 4, and a slope of 2. And let's try to make a nice straight line going through those guys. And let's color coordinate that as a green. Okay, so I'm also, excuse me, I'm yawning. I'm also seeing there's that little zone with a question mark right there. That might be part of our solution, but let's see. We have to graph this other one. Y equals 7 minus x. I will just rewrite that as negative x plus 7. So that means a y-intercept of 7. 6, 7, and a slope of negative 1. Okay, so it looks like this is going down here like this. Try to make a nice straight line. I missed it a little bit. Let's see if I can just bring it back in. Whoops. So a slope of 1, I think right there. Okay, cool. And let's have that one be, how about, like pink here. That's our pink line. Okay, so it looks like we are going for this zone right in here. Okay, that's interesting. We have to find the area of that zone. That's a quadrilateral. It doesn't look like it's a special quadrilateral. It looks like we have a couple different things going on there. So how can we figure this out? Here's what I'm going to do. I'm going to divide my quadrilateral into two pieces, each of which then is figure-outable. So I will have a triangle up top and a trapezoid down below. Does that look like a reasonable way to do it? I think so. Okay. So let's look at the top one first. So we have a base of 3. So area of a triangle is 1/2 base height. 1/2 times a base of 3 and a height of 2. This is my height right here. So that equals 3. Now this zone down below, area of a trapezoid is the average of the bases times the height. Other ways of writing that formula, but I always think it's easiest to remember just the average of the bases. So we have the bases need to be parallel. So those are the two bases, the sort of the top and bottoms of this trapezoid. So that's going to be, let's see, 1/2 times 3 plus, that's 7, I think, right? 2, 3, 4, 5, 7 times a height of 4. So that is going to equal 1/2 of 3 and 7 is 5, right? Average of 3 and 7. 5 times 4 is 20. So the overall area will be the sum of those, which is 23 square units. Nice. All right, let's look at this next one. Crickets can sometimes chirp more quickly when the temperature is higher. I don't know if you've ever noticed that. You collect a couple data points. First, when the temperature was 48 degrees, you count 32 chirps. Later, the temperature was 64, and you count 96 chirps. So a few things. Independent versus dependent, linear equation, and what if we counted 125 chirps? So I'm going to say the independent variable is the temperature because that's what causes the chirps to be at a particular rate. Okay, the chirps rely on the temperature. So let's define our variables here. Let's have x equal the temp, and let's have y equal chirps per minute. And so we have a couple data points. The temp was 48 and the chirps were 32. And the second point, the temp was 64 and the chirps were 96. Okay, and that definitely does confirm our thinking that they go faster when the temperature is warmer. Let's find a slope. 32 minus 96 over 48 minus 64. So it's a negative 64 up top and a negative 16 down below. So that has a quotient of 4. So our slope is 4. Think about what that means. That means every increase in temperature by 1 degree, the chirps per minute increase by 4. We need to find a y-intercept though. So how many chirps would it be for 0 degrees? Okay, and I'm assuming we're working with Fahrenheit, that we don't know for sure. Okay, but 0 degrees. Okay, so let's pick a point to use, and I'm just going to arbitrarily pick that point and the slope for x, y, and m. We can plug that in. So y is 32, m is 4, x is 48, plus our unknown b. Okay, so 4 times 48 is 192, and we subtract 192 from both sides, a negative 160. So there's something to think about. How many chirps per minute do the crickets do when it's 0 degrees? They chirp negative 160 chirps per minute. Doesn't make any sense in the real scenario, right? But we still need that b value to adjust our equation to make sure our line goes through these 2 points. Okay? So we have an equation now. Y equals 4x minus 160, so that's good. And we counted 125 chirps. So y equals 4 times 125 minus 160. And let's just go ahead and do that math. We get 340 chirps per minute. I think I made a mistake. Right? Anyone notice it? Y is chirps per minute, right? And hopefully you notice that as well. So I love making mistakes. That's how we learn. I was rushing a little bit, I think. So I can see here, I said y is chirps per minute, so that 125 should be y, okay? I was about to get 360 something or other, 340. The answer didn't make sense, so I went back and thought about it some more. So let's do this correctly. So 125 equals 4 times our unknown temperature minus 160. Okay, so let's add 160 to both sides. So 285 equals 4x, and we could divide both sides by 4. So 71.25 equals x. And let's think about, does that make sense? 125 chirps. It's bigger than each of the numbers we've seen so far for chirp, so it seems like it checks out. It seems like it makes sense. A little over 71 degrees. Phew, we did it. Nice. That's a good place to stop.